What we're trying to prove here is that if B is the inverse of A, then A has to be the inverse of B. Since we know that AB is equal to I, this means that A is invertible, meaning that A has full rank. Now we're going to let Bx equals to 0, and we're going to multiply this equation across by A to get A of Bx is equal to 0. But we know that AB is equal to the identity matrix. So this here is just the identity matrix, meaning that x is equal to 0. This means that the columns of B are linearly independent. If the columns of B are linearly independent, that means that B is of full rank. If B is of full rank, then we know that means that B is invertible, meaning that there is some matrix X such that Bx is equal to the identity matrix. So if we were to consider the product of B times the matrix A, that's just the equivalent of BA times the identity matrix, because if you multiply a matrix by the identity matrix, it stays the same. But we know that we can multiply that I is equal to Bx. So this gives us BA times Bx, because we had the identity matrix here, and the identity matrix is equal to Bx, so we just substitute in Bx for I. But since AB is equal to I, that means that we have Bix. But if you multiply any matrix by the identity matrix, the result stays the same, meaning that we have Bx here as well. This means that the matrix BA is equal to Bx, meaning that the matrix A has to be the identity matrix. Or sorry, that the product B of A is equal to the identity matrix. This means that A is the inverse of B, which is exactly what we were trying to prove.